Okay, hi everyone. I hope you had a good lunch. Our next speaker for this afternoon is Claudia Miller, and she'll be telling who's from Syracuse University, and she'll be telling us a little bit about graded free resolutions.
Yeah.
Okay.
Thank you. So my charge was to, number one, speak only at the level that someone could understand it with 1 year of algebra. So I'm not assuming commutative algebra. So those of you who know a lot more should just have patience. But I am going through the graded version, which some of you are not as exposed to if you go to a place that does everything locally. But anyway, so this first talk is going to be very down to earth. Okay, and my general task was homological algebra, which is too big a subject. So I am just going to talk about resolutions. I'm talking about the things that are useful for the people lecturing next week, specifically Christine Burkesh. Okay. So graded free resolutions. And so as such, I'm not even assuming that people know algebraic geometry or anything. So today is going to be very straightforward, and so is Wednesday. And then the third talk, I will say a little bit crazier things, but also some down-to-earth things. It'll be a mixture of things for people who know more and people who don't, okay? All right. So to start with, in algebraic geometry, you study things called a variety, which is really the vanishing set of some polynomials, some given set of polynomials. And then on the algebraic side, you talk about the coordinate ring, which is really just the ring of polynomial polyfunctions on this variety. So for example, you might talk about the vanishing set of the following polynomial: y squared minus x squared times x plus 1. So in other words, we're setting this equal to 0 and graphing it, x, y, and well, it's symmetric in y because you have a y squared, so plus or minus y satisfies it. It crosses y equals 0 at 0 twice and at minus 1 once. Minus 1, it crosses once. At 0, it crosses twice. Whoops. So that's what it looks like. Okay, and that's called a node, and that's a famous thing. So we study things using the equations and try to understand the geometry of them, even if we can't graph them. If they're in more variables, higher dimensions, more polynomials, and you can't graph it. So what does the algebra reflect? So what's the ring of functions on this? So the ring R that we're interested in here is, first place, you look at the polynomial ring. So those are all the polynomials in variables x and y. And every single polynomial, if you look at it just at these points, gives you a function, right? But there is one function that is boring on here. This function, y squared minus x squared x plus 1, is 0 on this whole curve, because that's the function that we set equal to 0 to define the curve. So that function is boring. So we mod out by the ideal y squared minus x squared x plus 1. And by Hilbert-Nullstellen's, you're really supposed to mod out by the radical of this ideal, but whatever. In this case, that's all. So any functions that are multiples of this are 0. It's the same as the 0 function on here. And this turns out to give you the distinct polynomial functions on the ring. So we study the rings versus the algebra. Okay, to go a little further, this is kind of set up for my third lecture, but a little bit we might, well, yeah, for my third lecture. So you might also have something called a sheaf. This is a curly F. And so that's some kind of a structure that you can build on that variety. Oh, I forgot to give the variety a name. I'm going to call it X. X equals this vanishing set. So it's a structure on X. It's something where, well, I'll say more on another day. It's something such that on every open set inside there, you attach a module, but the modules are all related to each other. In some sense, very often, in this case, for example, it's given by a single module, an R module, a single R module M over the ring of functions gives you a sheaf, and most sheaves kind of come from that in a sense that can be made precise. And even better, if M is projective or say a free module, then the structure that you build can be very nice. So here's the curve I had. You can think of a projective module or a free module as giving you at each point some free module locally. So it's like you have a vector bundle where you've attached a line. It should be an infinite line. You've attached, say, a rank one would be you've attached a line in every place. And you have like this strip. It's infinite, actually, and I just didn't draw it. So in some sense, projective modules and free modules correspond to structures on something that are locally trivial. They're locally like the base thing, plus something very simple, like a free something. Okay, so that is, I'm just trying to tell you why projective and free modules are interesting. Okay, and so to study these, being very vague, to study these kinds of geometric objects, we go to the algebraic side and we try to attach invariants that will reflect the geometry. So we'll attach invariants. And this is actually a very common thing. It's the same in topology, the same in anything. To study a space, you study the functions between such spaces, or just the functions, say, to the real numbers or to some field on the space. That's a very common way to study an object in many parts of mathematics. And then you start to also study structures on it that look like this, like bundles. Okay, so this is like a common way to understand something, is to build something on it, and that will help you understand the original thing better. All right, so one of the most important or basic even, are free resolutions or projective resolutions. So that is what I'm going to describe today. And in fact, they're not only the structure of them gives you a lot of information, but you can use them to build derived functors and cohomology theories, which, just like in topology, cohomology theories tell you things about your space. Okay, none of which I'm going to define this week. All right, so basics definition. If R is a commutative ring, oh, also, please, if you don't know what word I abbreviated or wrote, or if I said something and you just want me to repeat it because you spaced out, just stop me very fast. Please, just boom, stop me, okay? All right, R is a commutative ring, all of today. M is an R module. It will often be finitely generated, but not right now. So what we do is we put free modules. So I'm going to take a free module F0, mapping to M by a map called epsilon, and then by a map called boundary 1 or partial 1. I put another one, and I keep going for a while. And somewhere you'll have an Fi, and there'll be boundary I. And this might just go forever. Okay, so this guy, this thing, is a free resolution of M over R if each Fi is a free R module. What do we mean by that? It means Fi is like R to the Bi for some integer Bi. In other words, that's like R plus R plus R Bi times, and the order tuples are giving you the free module. So that's a free module with basis. So the basis of this would be E1, which is the vector 1, 0, 0, 0, 0, 0. E2, which is 0, 1, 0, da, da, da. And so on up to E. How many do I have? EBI. but that's going to be the standard basis for that free module. If you want to make a map from a free module, you just have to, a homomorphism, you just have to say where the basis goes, and you get a R homomorphism for module homomorphism from this free module. Universal property of free. Anyway, so you want each of the Fi to be free, and then you want that sequence to be exact that I've written on the board. Now, I'm not assuming homological algebra, so let me tell you what that means. Well, actually, how many of you know what exact means? How many of you do not know what exact sequence means? Don't be shy. Yeah. Okay, well, so then I'll just say it very fast. The image of partial I, or boundary I, is equal to the kernel of boundary I minus 1. But then I guess I should say something at the very end. Image of boundary 1 is kernel of epsilon, and epsilon is, image of epsilon is kernel of the next map, so it's the same as saying epsilon is surjective. Okay. And so in the process, in particular, you get that M is the co-kernel of the epsilon map. So it's, sorry, of the previous map. So it's F0 mod the kernel of epsilon, or F0 mod the image of boundary 1. That should be an ISO. Okay, so, and that's called the co-kernel. Co-ker of boundary 1. Co-kernel of boundary 1. Okay, good. Epsilon. What? No. Co-kernel of boundary 1. Okay, good. All right. We're going to write shorthand sometimes. We also write the following. Instead of writing all of F out, I write F dot to stand for the whole thing. And to signify, well, there's got to be this map epsilon from, that really means it's only coming from F0 to M. And to signify that that it's all exact and whatever, I'm going to put quasi-iso symbol here. If you know more homological algebra, you know what I mean, but that's what I'll write. And the boundary is called, quote, a differential. Also called a boundary map. So boundary. Okay, great. So first, I will tell you how to construct it. Again, I know that most of you know, but I don't care. But I tell you how to construct it. I'll tell you a few general facts. And then I'm going to spend the entire rest of the lecture doing one example twice, just to be, and how to read a Betti table. That's the most important part at the very end. Okay, so the construction. You start at the right end and you start looking for an F0 to map onto M. Okay, so step 1, let you choose generator. So let M1 up to M B0, whatever number that is, be a set of generators of M as an R module. Yes. No, so it could be infinite. So B0 could be infinity. For next week, it's always going to be finite, so I don't really care. Yeah, good question. All right, I'll say finally generate eventually, but I just, okay, whatever. So then map, so B could be infinite. So map a free module, a free R module of, what's it say? Let's just say onto M as follows. So you just take F0 to be R to the B0, or really whatever cardinality basis you have. Epsilon to M, so you take the ith basis element, E sub I, which is really 0, 0, 0, 1, 0, 0, 0. And you map that basis element to that ith generator, Mi. Doesn't need to be countable either, so whatever. Okay, and there you go. So, and so this map is surjective by construction because you hit all the generators. Could be any set of generators. Oops. Let me leave this here. All right, and then you look at what you've got. And so now you want to make something exact that that the image of it is the kernel of this map. So you want to put an F1 here so that the image of F1 is the kernel of the next map. So in other words, I want to look at the kernel of epsilon and try to make it an image. So I'm just going to say step 2, repeat for kernel epsilon. So let's put the picture up. So I have so far F0 mapping on to M. Then I look inside of there at the kernel of epsilon. This inclusion I'm going to call I. Just the inclusion of the kernel into there. All right. And how am I going to hit this guy? Pick set of generators. So choose gens. Let's call them Z1 up to ZB1 or infinite, whatever. And then take a free module F1, which is really R to the B1, and map it onto this kernel. Let's call this map pi. That sends E1. Oh, sorry, this had E's, right? So I'm going to call this E1 prime. That goes to the generator Zi. So this free module with a basis, E1 prime through B1 prime, will hit all these generators. So this will be a surjection. Now I just take this composition here, I pi, and call it boundary 1. Okay. I'm going to check if it's exact. So what is the image of this map? Well, this is an inclusion, and it factors through here. So this is the same as the image of this map as a submodule. So the image of this map is the image of this map. This image of this map is this, because it was surjective. And that is, so therefore the image of this is the kernel of epsilon, like you want. So that's exact. I'll put that in the corner here. So by construction, the image of boundary 1 is, in fact, so this is because I is an inclusion, so it's 1-to-1. It's the same as the image of pi, and then that's the kernel of epsilon. So this is exact in this position F0. We're good. And then you just keep going. Any questions so far? I'll say keep going in a second. I guess. I'll say that next time. Okay, fine. The current, so notice one more thing, just to be complete. The kernel of epsilon is, just by definition, the set of all, the sum of Ri, Ei equals whatever, 1 to B0, such that, this is a set notation there, such that epsilon of this is 0. Well, what is epsilon of this? These are ring elements. These are the basis elements. So the ring elements drag along because it's an R homomorphism. The basis element EI went to MI. And you want that to be 0 for this to be in the kernel. So in other words, these formalize things that combinations of M that are 0. So these are formal expressions that give you the relations on the MIs, on the these were the generators of M. All right, so the very first step, we pick generators of M, and now we're looking at this kernel, but really what we're looking at is relations on these generators. We start with generators with the first map, then this map is telling us relations on the generators. The next map will tell us relation, and these relations were given by these ZJs. We just called them ZJs up there, but now I'm saying what they are explicitly. Next step will be the relations among the ZJs. So that will be relations among the relations of the generators. The next step will be the relations among the relations. Okay, so that is what the process of taking. Okay. Yeah.
This is a 3-board setup.
Yes.
So the optimal order is
Oh no.
middle, front, back. Middle board, put it up, bring the front down. Then use the front, then put that up. Then use the back board.
That's a good idea. So I'll try it. Where's the middle board? Here it is. Okay. Okay, let's do the middle board first.
Everyone knows. So do it next time.
But then you lose, okay, you have to not get more than one board behind. Yeah, well, but he's saying you only cover, as long as you're only one board behind.
That's just it. You'll always see the last.
I'll try it. Okay. Yeah, okay, I'll try it. So what we have now is M goes to 0. So epsilon, we have F0 that maps onto it. We have F1, 2, so on. So this is the kernel of epsilon here, including in and surjecting. Now we have the kernel of boundary 1, including surjecting. So this was boundary 1, boundary 2. And then you have the kernel of boundary 2, and you continue. Surjecting from whatever, F3, and you continue. So did I say continue somewhere? No. Okay, 3, repeat. Repeat to get this picture up above, okay? All right. A few comments. All right, there are 2 settings that we work in a lot. One of them is that the ring is local, which means it's Noetherian and, okay, I should say that, Noetherian, plus it has a unique maximal ideal, unique maximal, let's call it Curlian. All right, so that's a setting in geometry that if you want to focus near a point, whatever that means, okay? Or we look at the entire variety and you started with a polynomial ring that is a graded ring. And I'll talk more about graded rings in a minute, but let me just say now, the other setting is that R is the direct sum of some graded pieces, Ri, I equals 0 to infinity. And so this is what's going to be called standard graded. So by that, I mean that R0, I will sort of actually tell you in an example what this means if you haven't seen it, but a lot of you have, but still. So R0, I want to be a field, the degree 0 part, and then the maximal here, there is not only one maximal ideal, there are gazillions of maximal ideals most of the time, but the maximal ideal that I'm going to call M is really what people write homogeneous maximal ideal, HGS is homogeneous. And that is the positive degree part. So I bigger than 0, Ri. These are the 2 settings we have. And this one is obvious why we would study this from geometry, because, well, oh, it's not on the board anymore, because polynomial rings are like this. And when we look at a variety and we look at the coordinate ring on it, remember I said it was the polynomial ring mod something. And so a little bit later in the talk, I'll show you how the polynomial ring breaks up like this. So in geometry, this is a common setting. I myself work in this setting up here much more, but I'm lecturing in this setting because this is useful for this week and next week especially. Okay, so mostly we will be looking at the second one. And I'm going to run by some quick facts. Fact 1 is that for such a ring, for such R, well, I mean, I raised it if here, comma, okay. A finitely generated module F is free when at the same time, so if and only if it is projective. And if you don't know what projective is, it doesn't matter because our modules will be free. So, okay, but like the better way to talk about a lot of things is this. It's a little more general than free modules. Yes, okay. I forgot the word. Sorry. A finite generator R module, and I'll write graded. In fact, sometimes I'm just going to write GDD for graded. Yeah. So yes, it needs to be graded. Sorry, if the module needs to be graded for this to be true. Yes, and finally generated. Yep. Yes. Did I not say that? Thank you. Yes, I say it later in my notes and I forgot to say it here. Thank you. And generated as an algebra by R1 over R0. So the way we often write that is you're allowed R0, yes, finitely. Thank you. Finitely generated by its degree 1 piece. Well, so that's not completely true. Some people say it's standard gradient even if it's infinitely. It won't be Noetherian then. But some people use the word standard graded. I don't know. I'm always Noetherian. That's why I'm really not sure. Okay, I think it should be finitely generated we need it to be anyway. So, okay, good. So this is symbolically, it says that you're allowed as an algebra to multiply the things in degree 1 and get all the rest take sums with linear combinations with coefficients in R0. Once we do polynomial, this will make more sense to you. Yes, if it's new. I'll linger on this more in a little bit. Okay. Then fact 2 is, and I will say that M is finitely generated. Well, okay, or if you're in the graded case, it's finitely generated and graded. R module, then the following are equivalent. 1, if you are very careful how you resolve, and at each stage where you're taking generators of the thing you want to hit, you take a minimal set of generators, which in this case will also be a smallest set of generators. If you choose minimal set of gens is generators, at each step, the complex that you get, it's equivalent to having, sorry, my grammar's off, but you know what I mean. If you did this, it's the same as asking that the image of each differential is contained in the maximal ideal times the previous free module. So it will never hit a basis element or something that could be part of a basis. That is equivalent. And then if these hold, if this is a minimal thing, then if so, this is in some of the exercises, then F dot is unique up to ISO, meaning any other, if you do it, 2 people do it and choose different generators along the way, but choose minimal sets of generators, which are not unique, but like the same number of generators at each stage. Your 2 resolutions that you build, there will be a map between them that's an isomorphism. Sorry, couldn't hear you. Yeah. Homogeneous. Yeah. So homogeneous. Thank you. So you need to choose homogeneous generators. Yes.
I'm just getting clear on the grammar.
Yes.
Point 1, the minimal set of possibly homogeneous generators was chosen at each step.
Yeah, if this is true, then this is true. If you did this, then the image of your differentials will be an M. if you have this, then there exists, you can do, then, then it means your images of your boundaries are the basis elements, the images of the basis sets are giving you minimal sets of generators. Yeah, so not great grammar. So another way to say this, choose, is just the image of the basis of Fi for all I is giving a minimal set of generators of the previous kernel. Okay. All right, and so once you do that, it's actually unique. So, so this thing is then called up to isomorphism. I haven't told you what a map of complexes is. I can't do everything. So there's a map between the two, your resolution and your resolution. There's a map between them such that the squares commute and that they're isomorphic free modules, the same rank, and then isomorphism. Okay, then this is called, quote, the minimal. And you can say the word graded if you want in the graded situation. The minimal free, you can also not say it. The minimal free, because most people will know you mean this if you're in the graded case anyway. The minimal free resolution of M, and I guess you could say over R. So minimal free resolution. And I'm going to be lazy, and I'm going to write MFR most of the time for that. Minimal free resolution, minimal graded free resolution of M over R. Okay. All right. But since it's unique, we can start recording invariants from it. Well, the whole resolution is an invariant. So what is the point of a resolution? Well, there are many points. The very first point is you've usually replaced the module with a set for which you have a set of generators and weirdo relations. You sort of replace the module by free object, but it's not enough to replace it by one free object because it's not free. It's not isomorphic to a free object, but it keeps approximating how far it is from a free object. So it's sort of inductively checking how close it is to something free. Okay, so you've replaced M by its resolution without all the same information. Okay, so the first thing we can notice in there is that the ranks of the free modules are going to give you a nice invariant. So define the ith Betti number beta I or bi, depending on what mood you're in, to be the rank of the Fi as a free R module. Okay. Great. And they're like, okay, so what, you define something, but it turns out that this is like a really good thing to define because there's a lot you can say about Betti numbers that get you somewhere. Like sometimes it's easier to forget some information and keep some and actually get further. Okay. But before I move on, I'll tell you that there are several ways to talk about this. So another way to talk about it is, so leave a little space here, but if you take Fi, and this is like R to the bi, right? And you tensor it over R with K, where K is R mod that maximal ideal. This is called the residue field. So if you take the residue field and you tensor your free module over R with K, K is R mod M, it now becomes, it's like a direct sum of copies of R tensored over R with K, you get a direct sum of copies of K. So you get K to the bi. You get direct sum K plus K plus K plus K bi times. And now this is great because it's a vector space. And vector spaces are sometimes nicer to deal with. Good, but so this has the same rank as this, right? So let me write the word rank here. Rank now as a vector space of this, which is the rank of K to the bi as a vector space rank. Okay, so who cares except that what happened when you took this resolution, whose differentials land in the maximal ideal. Now you go mod the maximal ideal. You get a resolution, well, you get a complex whose maps are now 0 because you got rid of m. You modded out by m. So now this thing is a new complex whose differential, so the differential of this complex, I'll put a differential bar. So the differential of this new complex is 0. Okay? That means you have fi tensor k, fi minus 1 tensor k, and 0 maps between them. That means that this whole thing is the same as rank over k of the homology of that complex. Let me just write that down first. Some of you don't know what that is. Maybe many of you do. Homology means, this is the homology. So this is like the, I should take it in spot I. This is in spot I. So let me take the I homology. So I just put an I subscript here. This is homology, which is defined to be the kernel of differential I mod the image of the map coming in differential I plus 1. But I guess I'm in this tensored complex, so I'll put a bar over it. Sorry, whatever. Yes?
First, take the minimal free resolution and tensor with k in each mod.
Yeah. Let me write it out.
Yeah.
Let me write it out a little bit. Let me write it out. So I really have now like F2 tensor over R with K, F1 tensor over R with K, F0 tensor over R with K. And I'm going to drop the M. So I'll just put a 0. And it keeps going like this. But now the maps in F landed in the maximal ideal. So now the maps are actually literally 0. So wherever you are standing, this is differential 2 bar. This is differential 1 bar. They're all 0. So we know that the Betti number is the rank of this module, but it's also the same as the homology here. What is the homology standing here? It's the kernel of the next map. The next map is the 0 map. So everything is in the kernel. Everything goes to 0. So this whole thing, mod the image of the previous map, but that's 0. So mod nothing. So it's just what's sitting here. Everything here goes to 0 and nothing is in the image. So this is the same as the kernel mod the image in that spot. Okay. So you're getting the same as the rank of homology of F tensor K. And those of you who have seen homological algebra know that this homology module has a name called Tor. So it's the derived functor of torsion in some sense. It's the Tor over the ring I, the I Tor of the module M that you resolve and the module K. So if you haven't seen that, don't worry about it, but someday you'll see Tor and you'll know what this is. So the way you make a Tor, it's the derived functor of tensor product, is you take the module, you replace it by resolution, tensor with the other guy, that tensoring is the functor, and then take kernel mod image everywhere. Okay, I'm not trying to scare you or anything, I'm just telling you other versions of Betti numbers. It's not that important for what we're gonna do, okay? Yes?
So what you've just written is a couple of times. Is that still going all the way back equals to beta I?
Yeah, yes. The beta I is the rank of Fi over R, which is the rank of this tensor down complex over K, but this tensor down complex has 0 differential, so it's equal to its homology. The homology is called Tor.
And there's a couple missing I's.
Yeah, there probably are. There's an I here. All the H's should have I's. Yeah. F, I don't write bullet. F dot. F dot is the entire complex F. Yeah. I don't always write the dot. Good? Okay. Uh-oh. Yeah, well. Okay. Oh, this is going to have to speed up now. So, okay, so I'm going to do one example, and you're going to do more examples in the problem session. And then I'm going to do it again very fast with some shifts in it. And then I'm going to talk about how to encode that information in a Betti table. So the rest of the talk is this example. Example 1. So I'm going to call the ring R. I'm going to call it S momentarily because it's just a polynomial ring, and we like calling polynomial rings S because they are symmetric algebras of a vector space. So okay, so it's the polynomial ring in 2 variables. I'm going to take the ideal to be the ideal generated by x cubed, comma, xy, and I want to find MFR, the minimal free resolution of S mod I over R, S mod I over S. Okay, so I'm going to take, and I want to map something onto S mod I. But as an S module, this is generated by the element 1. So I'm just going to take S to the 1, map its basis element, which I usually just call 1, and map it to 1. That's not a problem. Okay, now we're supposed to take the kernel. So this is the epsilon map. Free module onto the, I'm picking a free module of rank 1 and mapping it onto my module. Okay, because it has just 1 generator, so I only need 1 free module to 1 rank free module. Take the kernel. What goes to 0 under S to S mod I? I, right? So the kernel of epsilon is I. It's generated by 2 things, x cubed and xy. So it's 2 generated. So I need a rank 2 module here. S to the 2. S to the 2 means S plus S. Okay, it has 2 basis elements, E1 and E2. I'm going to map E1 to x cubed. I'm going to map E2 to xy. If you map a basis, universal property tells you get a map from an S linear map from the free module to there. So it takes the basis element, the first basis element to here, the second one to here. You could think of these as multiplied by 1. That's the basis element here. And in those bases, E1, E2, and 1, you can write this matrix by the images. The columns should be the images of the basis. So the first basis element, E1, goes to x cubed times 1, times the basis here. So it's x cubed in the matrix, the first column. The columns are the images of the basis elements. A2 goes to xy. So I'll put in the second column, I'll put in xy. So these are just the 2 columns. And they go to these multiples of the basis element. Great. What is the kernel of this map? Kernel. Oh, sorry. What is this map called? Boundary 1. That's the matrix of the map. Okay, what is the kernel of boundary 1? So I'm going to write it out for the people for whom it might be new. Kernel of epsilon is the set of all things in S2. So that's like S1, E1 plus S2, E2, such that if you apply epsilon to them, they go to 0. Yes, I do want kernel of boundary 1. Thank you. I'm in the wrong position. Kernel of boundary 1. Thank you. All right, so let's do boundary 1 of this. It's an S module map, so the S's just pull out. What was the image of E1? X cubed plus S2 xy. Okay, and I want that to equal 0 for it to be in the kernel. Okay, so now you just start guessing. What can you put here and here to make this equal to 0? All right, if I put a y here and an x squared and I subtract, so I'm going to put a minus y. This is just I can't explain to you why, but this is my favorite thing. I put a y minus y here. Minus y times x cubed and x squared times xy is 0. Good. So this, and that turns out to be the only possibility. And this and multiples of it. So this is generated by minus y e1 plus x squared e2. Okay. And I like to write that as a vector in the basis. The basis is e1, e2. So why not write it as a vector in that basis like this? Okay, so that's what that is. So now I need a free module mapping to that. Oh my goodness, I have 4 minutes. I'm not going to make it. Let's go as fast as possible. We'll see. Okay. All right. So then I'm going to actually go back up here and modify this diagram. So to map onto here, there's only one kernel element. So I just need S1. And its kernel, I'm going to call it E. And it's going to go to this lovely element, negative y x squared here. So I've got just one basis element. It goes to that. Writing that as this column of the matrix in terms of the basis E1, E2, I get that column. Good. Next map. If you think about it, what element of S multiplies this to 0? So what combination of the columns of this is 0? There's nothing. It's a domain. You can't multiply this by anything and get 0 except 0. The kernel is 0. So I can map 0 to that and 0. So the resolution ended. Okay? And the matrix, the way I write the matrix is the columns are the images of the basis elements. So E went to this generated the kernel. See, the kernel of this map we just computed was this one vector. This is really minus y E1 plus x squared E2. That's the one thing that's in the kernel. So I make a free module of rank 1 and I map it to that. Yes? Yeah, I know. You will learn from Fred how to justify what the kernel, that's the entire kernel. Okay. Me, I just guess. And you will also learn how to use the computer program Macaulay in my problem session to compute this. But what they're using is Fred's method. Well, he didn't invent it, but you know. Okay, good. All right, so now I want to quickly tell you about graded free resolutions. So maybe I'll just do what I can, and then the Betti table part I'll just talk about next time. We can't do those problems yet. All right, so the ring S, which is in this case k of xy, is graded, which means it has a degree 0 part, which is degrees is just the constants. It has a degree 1 part, which is the vector space given by x and y in all combinations. It has degree 2 monomials, which are like x squared, xy, and y squared. So here I mean the vector space given by this with this basis, and so on. And so we call this here degree 0. This stuff is all degree, this vector space is degree 1 stuff. This is degree 2 stuff. So I write this as S sub 0 plus S sub 1 plus S sub 2, and so on. So the polynomial ring has graded pieces that have these graded degrees. And so there we write the degree DEG for degree. Okay, so let's take that resolution that we have and actually write in the degrees of the maps. So in this resolution that I wrote, I want the differentials in the resolution and also the epsilon map to be of degree 0. So how are we going to do that? So let's look at the resolution again. I have S mod I. I have S mapping onto it. 1 goes to 1. That's a degree 0 to a degree 0 element. It's a degree 0 map. Okay. S1I is not, S mod I is an ideal. So S mod I, oh, I is homogeneous. I is generated by homogeneous elements. Then, yeah, so if I is generated by homogeneous elements, then the quotient again has a grading. Okay. Right, so then the next map took E1 to x cubed, and E2 got sent to xy, I believe. Yes? Okay, so it's really coming from S2 with E1, E2, but I'm going to write it as SE1 direct sum SE2 times the base, write the basis elements out. And then this basis element I called E, and E got sent to minus y E1 plus x squared E2, right? Okay, so as such, I would like this to be a degree 0 map. So x cubed has degree 3. So E1 has degree 3. All right, so let me start putting that in green. So this guy here has degree 3. E2 has to have degree 2 because it maps to a degree 2 element. And what does E have? It maps to this element, which has degree, y has degree 1, E1 has degree 3. So this has degree 1, this has degree 3. You're multiplying together, it totally has degree 4. So E has to have degree 4. Okay, goes to 0. And then I'll tell you this last thing and then I will stop. Is that we rewrite that so this is like a free S module of rank 1, but it's sitting in a weird degree. The generator, the basis element E1, is sitting in degree 3. Okay, so I'm going to write S E1. So that's like S, but with generator in degree 3. So what we write is S shifted by -3. So what does that really mean? That means S shifted by n sitting in degree I is S sub n plus I. So in other words, the one element of this ring should be sitting in degree 3. I want the base element to be sitting in degree 3. So let's check this ring in degree 3. S minus 3 sitting in degree 3 is -3 plus 3 is S0. And that contains the element 1, the basis element. So the basis element can either be called E1 or it can just be called like S shifted, but it's thought of, the 1 is thought of as sitting in degree 3 now instead of degree 0. But it's written -3, the shift. Okay, so now I'm going to rewrite this really quickly. Instead of S minus 1, we can write S, what was the degree of E1? 3. -3. Instead of SE2, I can write S degree -2. And what was the degree of E? 4. So this is S -4. That means S, but with the one element sitting in degree 4. It's shifted. You know, it's like I've taken that polynomial ring and I've just moved them over. So the S0 is thought of as being a degree 3 element, 3 part. S1 is thought of as sitting in degree 4. So the generator is always the element 1. 1 generates a ring. The generator is moved over and it sits in a positive degree if I shift it by a negative. So now these maps are degree 0 maps, and that is how we write them. And that's it. And I'm sorry I ran over.